In this example, we're going to use the method of characteristic roots to solve this recurrence relation given to us right here. And we're given some initial conditions. Let's just start with the recurrence relation now. So recall that if we're given a recurrence relation of the form a sub n equals 3, here let me write it in more general form. So if it's given to us as, say, c sub 1 a sub n minus 1 plus c sub 2 a sub n minus 2, then this is called a second degree recurrence relation with constant coefficients. And there's a formula for, or there's a method for solving this. The characteristic equation here, so the characteristic equation, this is the equation r squared minus c1 times r minus c2 equals 0. All right, and the solutions to this, so this will have solutions r1 and r2, and these can be any real numbers. In fact, they could even be complex numbers, right, if you're trying to solve a quadratic equation. But you can solve these. These will be complex numbers in general. So for us, if, let's say, if r1 is not equal to r2, and they're both real, right, then the solution, a sub n, is equal to some constant, call it alpha 1, times r1 to the power n, plus some other constant, alpha 2, times r2 to the power n. So in reality, the second degree, the second order recurrence relation is solved by a sum of geometric sequences. Okay, in some sense it's a sum of geometric sequences. All right, now the other case that we're going to care about is if r1 does equal r2, and of course it has to be real for that case to be true, right? Then the solution's a little different. It says that a sub n is equal to alpha 1 r1 to the power n, right? But now there's r2 is not different than r1, so we can't just use the same formula here. What we end up with is alpha 2 times n times r1 to the power n again. So instead of r2, r2 is the same as r1, right? So we replace r2 to the power n by another n times r1 to the power n. So these are the two solutions that we're going to care about. By the way, the complex fits in here, the complex solutions, but there are different ways to describe those. We're not going to work with any complex ones, at least not right now. So let's go back to our problem now. We need to write down the characteristic equation. All right, to do that, let's scroll back up and look at the recurrence relation itself. In this case, the c1, the coefficient on an minus 1, is 3, right? And c2 is equal to 4. And so we can write down our quadratic polynomial here, our quadratic equation. So the characteristic equation is then r squared minus 3r minus 4 equals 0. And the next job is to solve this for r. So this is a nice quadratic formula. This one, quadratic equation I should say, this one factors very nicely. It becomes r minus 4 times r plus 1. And so the two solutions are r1 equals 4 and r2 is equal to negative 1. It doesn't matter which one is r1 and which one is r2, but now we can write down our solution, but it's still going to have some unknown constants in it, right? So what is it going to be? It's going to be a sub n equals alpha 1 times 4 to the power n plus alpha 2 times negative 1 to the power n. And at this point we need to solve for alpha 1 and alpha 2. This is where the initial conditions come in. So the initial data up here. The initial data given to us was that a naught is equal to 2 and a1 is equal to negative 3. This is when n is equal to 0. This one occurs when n is equal to 1 in our solution equation that we just wrote down, right? So let's plug this information in and see if we can find alpha 1 and alpha 2. So alpha naught equal to 2 told us then that what? That 2, that's on the left-hand side, is equal to alpha 1 times 4 to the 0 plus alpha 2 times negative 1 to the 0. And of course, this just becomes 2 is equal to alpha 1 plus alpha 2. So there's one equation. The other equation we were told was that a sub 1 should be equal to negative 3. This is again when n equals 1. So now when we plug into our equation, we have a negative 3 on the left, and over here we have alpha 1 times 4 to the 1, 4 to the first power, plus alpha 2 times negative 1 to the first power. And so then our second equation can be written simply as negative 3 equals 4 alpha 1 minus alpha 2. And now we have a system of two equations and two unknowns. Now there are many, many ways to solve this one. This one is lined up for us pretty straightforwardly to be done by just what we call elimination method. Just add up the two equations. And when we do this, we see on the left-hand side we're left with negative 1. On the right-hand side we have 5 alpha 1. We're adding. And then over here these cancel, right? The alpha 2's cancel. And so this tells us straightforward that alpha 1 should equal negative 1/5. Once we know what alpha 1 is, it's part of our answer, right? We can plug into either one of these to solve for alpha 2. The first equation is very easy to solve for alpha 2. So that one says that alpha 2 is equal to 2 minus alpha 1, which is 2 plus 1/5, which is 11/5. Okay, and so this is our alpha 2. And now the last step is to just go back, plug those into our equation, and write down the solution to our recurrence relation. It is that a sub n is equal to negative 1/5, 4 to the power n, plus 11/5 times negative 1 to the power n. Alright, and this is good enough. You can leave it like this. You could, if you wanted to, combine all this together into a single fraction and write it as negative 4 to the power n plus 11 times negative 1 to the n all over 5. Alright, either one of those is fine. They are, of course, equivalent.